Okay, welcome to the 17th class meeting. So in the last class meeting of class meeting 16, I started with this notion of mean square periodicity. And we've seen the relation between mean square periodicity and cyclostationarity. From mean square periodicity, we've seen an interesting result like mean square periodic random process is Y-sense cyclostationary, and periodic random process is a very strong sense of cyclostationarity. So let's see. Sorry about that. Y-sense periodicity. So let me draw a block diagram, not block diagram, histogram. Sorry about that. It's kind of very confused myself. Just a second. So let me write it here. So let me review. So mean square periodicity was motivated by the periodic function, and where we usually started from this definition. There exists t positive and x of t equals x of t plus capital T for all t means periodicity. And we subtract the right-hand side from both of the sides and we square them. And they are all equivalent, right? Then here goes the definition of mean square periodicity. So we have mean square periodicity. Got it? So this was the definition. And we had a kind of too simple, but anyway, let's call it lemma because it's a result. And the first one is that the mean square periodicity. So x of t equals x of t plus capital T for all t in the mean square sense, which I didn't write last time, but whenever we have something like this, we call it mean square equivalence, mean square equality. So x of t equals x of t plus capital T for all t in the mean square sense implies, first one is that its mean process or mean path is periodic. And second one is that its autocorrelation function is what? Is sorry about that. Is periodic not only in T, but also in S, okay? And we may simply write it this way by introducing two parameters, M and N. Yeah. So let's see why this is true. Because last time I didn't derive the result, but just said that, okay, here is the Gemini's summary and you read it. And I found that one of the part is a little bit misleading. So let me provide you a proof. So the first one is that for the first part, we are going to use the fact that whenever we have a random variable, then we have this inequality. Why this is true for a random variable? Yeah, it's from just simply you will see like this, x squared fx dx, and you may just consider this, and you may wonder why this is true. Why? Why this is true? Anyway, so we are going to use this one. So think about this one. Yeah. So here we focus on that one corresponding this one. So here goes expectation of x of t minus x of t plus t squared. And this is definitely greater than or equal to 0. And we have expectation of x of t minus x of t plus capital T squared, which is by definition 0. So since some non-negative value is 0, lower bounded by 0 and upper bounded by 0 for all t, what does that mean? This means that expectation of x of t minus x of t plus t equals 0 for all t, which is same as mu sub x of t equals mu sub x of t plus capital T for all t. So the first part is proved. What was second part? Second part is a little bit tricky. And the Gemini summary was very intuitive. And I also tried to resort to that. And last time after the recording was stopped, I little bit murmured because it was not that vigorous. So here, let me show you. We also have one result like this. So whenever you have a product of two random variables and then you take the expectation, if you square it, then what do you have? You have Schwarz inequality. So you have x squares expectation times y squares expectation that upper bounds this product. So it's similar to A, you have two vectors in a product, it's upper bounded by auto inner product and auto inner product of B. And you may just, if you prefer this notation, then you have square root A, B, something like that. Am I right? Right? So I just said squared. No, we don't need this. So you may say that if you square this one, then you have squares. Got it? This is Schwarz inequality. So by this inequality, we have, again, expectation of x of t. And here goes the trick. We have x of s minus x of s plus t, if I remember correctly. Am I right? Just a second. Yeah, I believe I'm correct. So, yeah. So we start from this one, squared. Yeah. That, again, we have a lower bound 0 because it's the something squared. And we have, am I right? Yeah, just a second. Something's not correct. Yeah, just a second, just a second. Yeah. I don't need squaring, I believe. Okay. Yeah, okay. I don't need squaring. And so let me revise it. So assuming they are real. Okay, real. Yeah, just a second. Why this is, yeah. Very confusing. So let me just take the absolute values back. Anyway, So we have expectation of x of t squared and expectation of x of s minus x of s plus t squared. Am I right? And this holds, of course, for all t and s pair. And we know that this is by definition of mean square periodicity. This equals 0 for all s. So again, that is also 0 for all t and s. So here goes a step. So this part is 0 for all s, but that part is 0 for all t and s. Right? That's why this is 0 for all t comma s. Now we take the absolute value square off to have expectation of x of t, x of s minus x of s plus t equals 0. Or if we have a complex valued one, we may put conjugation here without loss of generality. Yeah, so we have eventually correlation, autocorrelation function equals this one. Got it? So do you have it? So I assume the x and y are complex valued random variables. So I put conjugation here. Probably I need to take the Hermitian transposition. Yeah. And everything else looks correct. Okay, let me see. Yeah, no problem. Yeah. So we have here one of the desired result. And now we can do the same thing because we can replace this one as this part as x of s and t plus capital T. So similarly, we have t plus capital T s for all t and s. And these two leads to the autocorrelation function equals t plus mt, s plus nt for all t and s and for all m and n. Got it? Yeah. And we compared it with cyclostationarity to have this Venn diagram. So here goes the Venn diagram, the set of all second order random processes, of course, continuous time in this case. And we have what the mean square periodicity implies y sense periodicity implies y sense cyclostationarity. So we have here ms periodicity, y sense periodicity, and y sense cyclostationarity. Got it? And the question was, what about the notion of mean square stationarity? Probably this is motivated by this Venn diagram. So we have y sense stationarity and some strict sense stationarity. So as far as we have something like wide sense periodicity, then it could be okay to consider y sense stationarity and mean square stationarity. So the question was, what would be the definition of mean square stationarity of a random process, and what would be the property of it? And after the video was off in the last class meeting, I said something like this. So mean square periodicity could be defined this way. And this is motivated by the fact that suppose x of t equals x of t minus tau for all t and tau. What does that mean? They are equal, right? It's a constant function. Am I right? And then we may subtract, and we may also square it. And actually, this becomes more generalized or loosened if we replace this minus tau as minus capital T or plus capital T to have our mean square periodicity back. So that's why I said this definition, plus tau or negative tau doesn't matter, may serve so-called mean square stationarity over a random process. And actually, its property is very similar to what I just derived for the mean square periodic random process. By following the same procedure, we can show that just replace plus t as minus tau. Then you first have its mean path is constant. And second, your autocorrelation function is, just a second, this is not correct. Okay. Yeah, this is y sense station. Yeah, just a second. Just a second. Yeah. So implies these two results. So mean square stationarity implies y sense stationarity as we know. Okay, but they are different. In this case of mean square periodicity, y sense periodicity is very very close property. However, this mean square stationarity, if we define this way, is quite small one. Stationarity. And I've decided to talk a little bit about this one. So, do you have an example of y sense stationary random process that is not trivial? Of course, you know, for example, y sense stationary Gaussian random process with some non-flat power spectral density. So you know n of t, y-sense station is Gaussian, and its power spectral density. Flat is okay, something like this, for example. Then what kind of mean and autocorrelation function does this n of t has? Of course, in this case, since there is no direct delta component, if in that case, the mean process is 0 for all t. And what about autocorrelation function? It's a function of t minus s. Here, r sub n is Abusov notation. This function is different from this two-dimensional function. And that one, as a function of tau, may look like some function like this, right? However, if you see mean square stationarity, then we have something weird. First, this is okay. The mean is constant. It could have mean 0. But if you just calculate the autocorrelation, if you try to calculate the autocorrelation function, then you have something strange, because why there is no, yeah, I cannot find what I wrote. Yeah, just a second. Where is, oh, okay, here it goes. Yeah, so here goes the proof. So we have mean square stationarity possibly defined this way. And mean square stationarity implies y-sense stationarity because first, following the same procedure, we have constant mean. And for the autocorrelation function, we consider the expectation of this product x of t and x of s minus x of s minus any tau. Then we have Schwarz inequality. And here, this is 0 by definition. And we have this holds for all t, s, and tau. And here goes something interesting. We may not only by choosing this, so if you product these two, then you have that one. And if you multiply these two, you have that one. Since this holds for all t, s, and tau, actually, you can replace this one with any value. What does that mean? We have a very serious trouble, actually. Not only the autocorrelation is a function of time difference, actually autocorrelation function itself does not change. Got it? So if this is a constant function, like some sigma square, right? Still, it's a function of t minus tau. In that sense, if we define mean square stationarity, it becomes y-sense stationary, but it's a very, very strange one. Then what kind of random process it is? It's just something like this. Random process x of t equals a random variable x for all t. So for example, if x could be a Gaussian random variable, then what is your sample path? Constant, always. But this sample path may differ depending on your generation. But in reality, what is this one? This is a deterministic random process, so that if you observe past values, then you can deterministically find the future values. So it does not have so-called ergodicity. But anyway, mathematically, this is a legitimate random process. And what do we have? This is strict sense stationary, actually. Ready? So here we have strict sense stationarity. And of course, some strict sense stationary random processes may have time varying autocorrelation function, something like that, because it just says that your translation of origin doesn't matter. But this mean square stationarity, if we define this way, is a very, very, very special random process. So probably people haven't found any usefulness of defining such a random process by giving something like mean square periodicity. Anyway, the reason why I explained this one is that the question was very entertaining. And also, the proof is related to the derivation of the property of a mean square periodic random process. And also, I wanted to talk more about the mean square periodicity. So if the so-called mean square stationarity doesn't make much sense, its slight change mean square periodicity may not have much usefulness, but actually that has much usefulness. That's what I want to say. So the difference is that, as you see here, if we define mean square periodicity, actually we just have a single random variable. However, if we have mean square periodicity, this kind of thing is possible. For example, sample path is a periodic function with period t. So here is the mean of the sample path, for example. This is a sample path that is periodic. And here is another sample path that is also periodic, something like that. And we may still say that, okay, so what? In this case, we may have very much different sample paths, and actually we have what? We have countably infinitely many random variables still. And this mean square periodic random process may be generated by a very special time-limited random process. So it's like, suppose we only can observe a finite interval of a random process and want to do some signal processing, like estimation or detection of something. In that case, we may regard this random process as a time-limited random process, even if originally it is not time-limited. Anyway, we only can observe x of t. Another one is that we can periodically extend this one to have a periodic random process. Now, t could be any number. Sometimes this kind of periodic extension gives us much freedom to analyze it, because whenever we observe periodicity, we may apply Fourier analysis, especially Fourier series analysis. So we may consider Fourier series of each sample path and find something. Actually, that is the idea of KL expansion. So before we move back to our study on spectrally correlated random processes, let me remind you about the KL expansion and related Mercer's theorem and other decompositions. So here we have a time-limited of course, second order random process x of t. Just for convenience, let's focus on some interval of length capital T. Here capital T is not period, just an interval. And we have, for example, expectation of x of t equals mu x of t for t0 to capital T. And we have autocorrelation function. Also, T and S defined only on this time interval. Now, let's consider an interesting approach to this one. What is this one, by the way? It's a linear filtering of the function v sub I of t using what? Using this impulse response type thing. And this is, of course, called the kernel. And what if the output, so it's like you have v sub I of t goes into LTV filter with impulse response RxSTS. Got it? And TNS time limited. Yeah. And 0 otherwise, or yeah, let's think in this way. Or you may limit this one, like Vi of t is 0 if for t less than 0 and t greater than capital T. Yeah, if you view this way, then no problem, right? You have usually the linear filter integrates from negative infinity to positive infinity. But here, if we restrict our function, input function to time limited function, then this is naturally true, right? And what if this is proportional to the input itself? And of course, t is also limited to 0 to t. And some of you may wonder why we think about this one. That is because in linear system, because this can be viewed as such a linear time-varying filtering, right? Or just simply linear filtering. We may, not always, but we may exploit so-called eigenstructure of the linear transformation. So if we can find the pair of lambda sub lambda sub I and V sub I, then what? What do we say? We call lambda sub I is an eigenfunction, and V sub I is the corresponding eigenfunction. This is eigenvalue, and this is eigenfunction. Moreover, we know that this Rx XTS is what? Is a kind of Hermitian symmetrical function. Why? Why is it so? We just use the commutativity of the multiplication, right? So we just change the order. And by definition, this is what? This is that one. Got it? So we have Hermitian symmetry. This is very similar to like some matrix is Hermitian symmetrical. Am I right? The ij positions value and ji positions value has conjugate pair. They are conjugate pair, right? And what else do we have? We have very interesting property like we multiply any function a of t then what do we have? What do we have in this case? Am I right? Just a second. Yeah, I believe I'm correct. Yeah, just a second, just a second. Yeah, in that case, we have, am I right? No, just a second. Something's not correct. Yeah. So think about the right-hand side. So you multiply x of t, the time-limited random process, with some function a of t, a conjugate of t, and you integrate. Then you usually have a complex number, random variable. Now you take the magnitude square and take the expectation. Then what do you have? You have non-negativity for all t. Now, what about you expand this one? So you choose another random variable. So another variable. Of course, you can write it this way first, right? However, in order to combine these two, you must choose different integration variable. So you may choose some s, right? Then eventually you have double integration and a conjugate of t. And this is simply autocorrelation function. And you have as dt ds. That's why this is non-negative for all choice of t and s. Got it? So you have conjugate symmetry and positive semi-definiteness in this case. Am I right? Yeah. So what do you want to use? Because of the parallelism in the linear algebra, when you have a Hermitian symmetrical positive semi-definite matrix, then you want to do orthonormal eigen decomposition. So what does that mean? If you can find the eigenvalue and eigenvector pairs in this case, actually, due to the property of this kernel of so-called the Fredholm integral equation, that is the name of this equation, Fredholm integral equation, you may find a pair of eigenvalues and eigenvectors where especially you have orthonormal eigenfunctions. So vi of t, vj of t integrated over the interval of length t gives you delta ij, which means that each v sub I eigenfunction has norm 1 as a function, and different eigenfunctions are orthogonal because different ij gives you 0. So we exactly follow what we've done in the eigen decomposition of a Hermitian symmetric semi-definite, positive semi-definite definiteness. So we may have the decomposition of this autocorrelation function like this. So lambda sub I, V sub I of t, V sub I of s conjugate. And confer something like lambda I, Vi, Bi, Hermitian transposition. Got it? You had the eigen decomposition like this. Probably you are more familiar with this notation, right? So diagonal capital lambda matrix, and you have unitary matrix V that contains orthonormal vectors V sub i's. Got it? So this is exact parallelism. If you cannot justify very rigorously mathematically, just remind you already accept this orthonormal eigen decomposition as the truth. So you can do the same thing. Now, what's interesting in that? The interesting part comes here. Now, think about a random vector x, okay, that has mean mu and covariance matrix C, right? If you want CXX. Now, what kind of transformation matrix will give you Y that has, sorry about that. Something like this. So can you make the correlation at the output zero, correlation coefficients zero between the components of output? So it's similar to whitening, but not exact, but anyway. So can you consider some transformation? And actually, the Hermitian symmetrical positive semi-definiteness of the covariance function, covariance matrix, actually gives us a hint, because we may consider a decomposition like this. So we may decompose the covariance matrix as unitary diagonal, unitary Hermitian, and what we do is this one. So we take these V's and think about V Hermitian X as Y first. Don't ask why, because it gives us my desired result. So expectation of Y is simply V Hermitian mu X, right? What about the covariance matrix? Then what do you have? You have V Hermitian and covariance of X, B. And you have lambda. Got it? So the interesting idea is that you may find some transformation that makes your output uncorrelated. And this may find very usefulness because in many cases, our zero mean part of X could be Gaussian. In that case, uncorrelatedness means independence, right? And another one is this one. Now, from this idea, since V is unitary matrix, what do we have if we multiply V to the left-hand side? We have X equals Vy. What does that mean? From some uncorrelated, some random vector with uncorrelated components, we may construct our desired original signal X. And moreover, we may do something like this. Suppose we have motivated by this one. So we insert V Hermitian V here. As first one, we may consider the square root of lambda because lambda is has non-negative diagonal components. So we may divide lambda as lambda raised to the power of half and lambda square root of lambda. And we put V Hermitian V. In that case, we have what? We have, we may use that one instead of V Hermitian, V. So now we may consider whitening filter. Then what? So actually we have the inverse of this one. Got it? Inverse of this one. If we don't have lambda raised to the power of half, then we have V inverse, which is V Hermitian. That's why here. This is V inverse. And this is simply V lambda 1/2 inverse. Got it? And what about Z? We may have some mean vector. But covariance is now what? Covariance matrix is the identity matrix. What does that mean now? We have Z times so Z pre-multiplied by V lambda raised to the power of 1/2 equals X. So this is the key actually. Now we can start from, except the mean part, we can start from what? Start from a white noise, uncorrelated, having uncorrelated components with the same variance. And then we construct vector X. And this is what? What about this one? This is just a second. Lambda B, B, B. Lambda N, use I, and I, Z, I. Okay, got it? So the vector X, a random vector X, can be generated from uncorrelated random variables. Okay. You can show that, yeah, like this. So this is zi's are uncorrelated random variables with same variance, same unit variance. So you scale and then multiply a deterministic vector, v sub I. And this is actually very closely related to what we are going to study, the translation series representation of a cyclostationary random process. That's why I'm talking about this one. Anyway, this KL expansion is very, very important. So let's go back to our previous one. So you are very confused. This is what I remind you from the graduate level, probability and random processes. Okay, got it? So let me go back to this point. And surprisingly, we can do the same thing. So we have decomposed the autocorrelation function this way. And now we may have something like this. So here goes some vector z, and that is, again, that has some mean and covariance identity. Okay. So let me not doing this. Okay. So v1 of t, c1, v2 of t, c2, vn of t. If we have finite number of eigenvalues and eigenvectors, and then multiply lambda 1, lambda 2, lambda n, and x of t. So can you see the parallelism between these two? So if you have a time-limited random process that is time-limited, then as you've done for random vector, you can apply eigenanalysis and find a representation of the time-limited random process by using uncorrelated. These sub i's are uncorrelated. Uncorrelated random variables of unit variance and some eigenfunctions, orthonormal eigenfunctions. Got it? And of course, you know how to find the G sub i's as you've done here. Got it? So let me give you what are G sub i's. Conjugation. Since you may have countably infinite number of eigenvalues, got it? Because this one is same as Just not the addition. Sorry about that. One. Yeah. Got it? So this block can be rewritten this way. In the same form, you have, here goes x of t, then you have time varying filter to this time limited signal. Then you have the scaling part, and you have z sub i's. They are all uncorrelated. Got it? So as far as you know this very well, then no problem. Of course, in order to have this representation, you have to be able to solve this Fred-Hold'em integral equation. And actually, given an arbitrary time-limited random process, it's very hard to solve this one. So many numerical methods have been developed. The simplest one is to what? In this digital era, just divide this interval into many sub-intervals of same length, for example, and just assume that the autocorrelation function, in this case, that serves as a kernel function, as a smooth function. In that case, you just take the, for example, middle point. And then actually, what do you have? You exactly have this problem with very large size Hermitian symmetrical positive semi-definite matrix. So they are actually the same problem. Got it? Anyway, and you will see why I have reviewed this one soon, not immediately, probably next Monday. Anyway, so you have the idea, got it? Yeah. That's why this talking about mean square periodic random process is quite interesting. Here, mean square periodic random process may be just a simple periodic extension of this time-limited random process. So sometimes we do not just handle Y-sense stationary random processes, neither Y-sense cyclostationary random processes, but just time-limited random processes because our limitation of observation. And also, in reality, there is no negative infinity and positive infinity. So this may be quite interesting. And the lessons obtained in handling this time-limited random process is actually very useful when you think about cyclostationary random process because of the similarity. As you've seen, mean square periodicity implies what? Implies Y-sense cyclostationarity. Got it? Anyway, so we will see this, not today. Anyway, so let's talk more about the, we go back to the shift invariant subspace and also related notion of Nyquist criterion, orthogonality and bi-orthogonality, signal to noise ratio, signal to interference ratio, signal to interference plus noise ratio, zero forcing and MMSE. But let's focus on only these two. Got it? So we are going back to our very familiar notion of what? Nyquist criterion. What it is. So let's start from what is Nyquist criterion from the title. If you just search for Nyquist criterion, sometimes you find Nyquist criterion on uniform sampling. And if you say to LLM that the A is not the other one, and you will find some Nyquist criterion in control theory. And then eventually you will find out this Nyquist criterion for zero intersymbol interference. However, this zero intersymbol interference is very, very misleading notion unless you think about the SNR, SIR, and SINR, and also orthogonality and bi-orthogonality. But I'm not going to talk about them all today, but let me give you an idea. So the idea is like this. The Nyquist criterion is simply, very simply written this way. So if a pulse P of t satisfies this one, what does that mean? If m equals n, it's a positive constant. Okay? So let's put m equals n. Then what do you have? Actually, m equals n means you have the energy of the signal P equals C. So that's why C is positive. What if m different from n? You may choose m equals 0. In that case, you have you fix the first vector P of t, and you have conjugation and shift. So if you have some shift by n or integer multiple of it, then it's 0. So here, P of t satisfies the Nyquist criterion for 0 ISI if this holds. But still, you may wonder, hey, what is this capital T? So precisely speaking, you have to say that P of t satisfies the Nyquist criterion for 0 ISI when the symbol transmission rate is 1 over capital T. So you may need this one. And the problem of this definition is that actually, if you just present this one to a sophomore who haven't yet taken communications course, they never imagine what sub-area of electrical engineering requires this criterion because they have no idea what 0 ISI. And you even just delete this one, a Nyquist criterion, right? And this is motivated by our very special digital modulation format that is quite familiar with you. Just this one. Okay. So simply, this is data symbol, and P of t is transmit waveform. The problem is that actually we don't need this plus minus infinity. Sometimes we may need some finite length. So some cases, we just consider capital M symbols transmitted and talk about this definition. In that case, you may say that why we need all M and N. But in many cases, we just assume m and n can be any integer. But when we have finite number of m's, it's a little bit different, actually. But anyway. So let's just, for simplicity, think about infinite number of symbols. But this is not necessary. That's what I want to say. Actually, we just give up that one, but consider something like this. And you may really hate it. So here, this is modeled as a random process, right? Because data symbol is random. But here, I'm not saying X. So, as you see here, this Nyquist criteria may assume we have digital modulation. Or we may have what? Shift invariant subspace. It doesn't matter, actually. Our definition does not require digital modulation. It could be okay. We may, in underline, we may assume we are given some digitally modulated signal, or actually, we may have shift invariant subspace. That is a collection of all the signals that has finite energy but restricted to this form. Got it? And now, what does this mean? We have actually we may actually have this structure. What is it? It's a matched filter matched to the pulse, and sampler that takes sample at every t with, in this case, offset 0. Okay? If we change the offset, we may have a lot of difficulty, but anyway. So we assume this one, and what is our goal here? What is our goal here? The goal is that here, the output, let's say y sub I equals y sub m, actually. Y sub m equals d sub m in this case, or a sub m in that case. No other component. So we consider if it is a communication, digital communications, we assume this receiver. So we received x of t. We have a filter, LTI filter matched to the transmit pulse. So we have conjugation and time reverse. And we sample at every MT. And the mth output equals d sub m in this case. And now another one is that we may have a deterministic signal x of t. Now it's totally just signal processing idea. We have a matched filter, matched to p of t, and then we take the sample, we get a back. So actually, this is what? This generates a of n given x of t. You may say that. So we may have representation of x of t this way. Got it? So if the generator function satisfies the Nyquist criterion, then our A sub n sequence can be obtained this way, right? Or if you don't like this one, then let me redraw the block diagram using correlator. You may consider multiplying the delayed or advanced version of P conjugate of T and integrate, or if you don't like, you may just have the inner product operator. It depends on your choice. Got it? So you may assume that you have countably infinite number of correlators. That can be written as multiplier and integrator or inner product operators, right? Or mathematically equivalently, you have single matched filter sampled at every t. That doesn't matter. Got it? So the Nyquist criterion now, before probably Nyquist criterion for zero inter-symbol interference, if you just attached that one, is in the context of digital modulation only. But now, today, we have expanded that idea so that this Nyquist criterion, that symbol rate, how to say it, the shift, just for time t, okay? We may say that to combine both of the ideas, right? And this t could serve as the symbol period, or this t could be serve as amount of shift in the construction of your shift invariant subspace. Got it? But you need to specify t because P of t may satisfy this Nyquist criterion for a specific capital T, but it may not, or in general does not, for other t prime. So specifying this time parameter t is very important. Of course, if P of t satisfies Nyquist criterion for capital T, then it satisfies 2t, 3t, any integer multiple of t naturally. However, not for arbitrary t prime. Got it? Anyway, so in this way, now we have the idea that this Nyquist criterion, you may call it for zero ISI, or for the some also, how to say that, some also normal construction of your shift invariant subspace. Anyway, that assume this type of system to take the samples or to take the coefficients. This is very similar to what? Some system for Fourier analysis of a periodic signal, right? What you do is that you take a single period, and what do? You multiply Fourier basis and integrate to obtain the coefficient. And then you reconstruct the signal with summation, Fourier coefficient, and each basis function. The same structure, okay? So you need to have the idea that there are many similar representation techniques or synthesizing techniques of some very structured signals or random processes. And there are usually there are parallelism in random area and deterministic area, like this cyclostationary, very special cyclostationary signal. This is digital modulation, and shift invariant subspaces. Okay, it seems I have something more to say, but let me stop here and continue next Monday. Any questions?